Great, thanks for sharing that. I appreciate it. So the goal with implementing data science in an organization is to develop a process that leverages data to consistently add value to your contamination investigation. And that process will have strategy. So there are business questions that you need to answer. You need the right people, software, hardware, data, of course, and methods. And all of these require a balance in all of these in order to be successful at it. There are different facets of data science. So if you were going to plot yourself out on each of these, each of you are probably an expert in one of these axes, if not more than one. But you want to make sure as a group, as a team, you have all this ground covered. So there are things like data engineering, which is all the collection and cleaning, reformatting of data. Software development, it's typically not at the level of like a commercial software developer, but you typically do need some skills in a scripting language like Python or R. Even Excel macros can be really useful in order to get the most out of your data. Communication, really communicating the success, communicating your ultimate business goals are essential. Data visualization is one of those ways of communicating, but it's kind of a specialist field of its own. Machine learning, which we'll talk more about, and then domain knowledge. So domain knowledge, I'm sure we're all pretty strong at, but when you bring new people into the organization that might have high expertise in data science, they may have very little domain knowledge. And so building them up and increasing their capabilities there is really important. So that's good. So the next thing I'll talk to you about then is what we call the hierarchy of needs in data science. So lots of you are probably familiar with Maslow's pyramid, Maslow's hierarchy of our own needs and what we need to be healthy and survive. So this is kind of modeled after that. And so this is a lot of what we do as an industry is down in this bottom layer, instrumentation, logging, sensors. Everybody's really engaged and active in that domain. Even coming up the next level, structured and unstructured data storage, so databases and storing data, reports about our sites. But the industry as a whole is not really pushed to this top level. So in this top level, you find things like advertising and marketing, banking, defense and intel. I mean, these are kind of the top tier industries that are really using data science at a high level. And so one of the things that I'll want you to think about as we're going through is how can you take your organization up a level, wherever you are in this pyramid. What would it take to go to the next tier up? And so hopefully we'll give you some ideas and some techniques on how to do that in this talk so that you can implement it back in your organization. So one of the first things we think about is usually data. So commercial data can be a viable choice. It's generally higher quality, completeness when you buy from a data aggregator, and specificity to a particular data set. So if you're looking for that marketing data or environmental industry data, there are a number of vendors that will give you reports on the size of the market, how much is being spent. Those aggregators spend a lot of time pulling in information about this industry and other industries as well. So you can consider some other open alternatives as well. So a lot of our government agencies have data that you can mine and search through. Data.gov is a good place to start for US-based data. EPA has a very broad data set across the entire country, but at a fairly thin level. If you don't need to go very deep into individual data points or individual projects, EPA is a good place to start for a sort of holistic view. To get really granular and specific for a particular state, that state's Department of Environmental Quality is a good place. It's kind of a mixed bag on which states are really forthcoming with that information. I saw some folks from New Jersey. New Jersey is by far the top in terms of transparency and openness. They have an open database that's on the web that you can search and mine and pull data from. Very good database. Other states aren't quite there yet, and then there's a whole spectrum in between. For mapping data and geospatial data, OpenStreetMap, things like Google Maps and Bing Maps and things like that are out there as well. So think about alternative sources for data that aren't currently inside your organization. Another thing when we talk about modeling and data science and using algorithms to make predictions about data, one thing that I've observed over a long time doing this is that you always get better performance improvement from adding new variables and new types of data than you do spend improving an algorithm. So you can spend a lot of time tweaking an algorithm and trying new things and trying new techniques and only get really small incremental improvements. But adding new data types and new variables to it really can get these kind of really big jumps in your performance. Here's an example from an actual project I did. So what we're seeing here is false positive rates, and this is the number of cases. So as we look at an increasing number of cases, there's a small number of those that are false positives. So here we're doing a classification. We're trying to detect bad data in this data set. And so we're on kind of a steady incline here, but what we see is when we start to bring in this case, some geospatial variables, we saw a 24% improvement in the model's performance on false positive rate. Whereas when we tried different models applied to it, neural nets, regression trees, random forest, we only saw a 9% improvement by changing those different techniques. So this has been a constant throughout my work, and I've seen this phenomenon cited by other folks as well, that you get a much bigger bang for your buck by putting in the work to add new variables than by tweaking and messing around with different modeling techniques. So another question that comes up is about big data. And so I found these charts from a survey of data scientists over the years, looking at the largest data set that they've analyzed, or that they commonly analyze. And so I thought it was interesting. This is 2016 data, but the trend is sort of static over time. Really, the big data sets aren't that big, and so we're looking at on the order of gigabytes up to a terabyte for most problems. And even if you split it out by industry, the government, corporate environment, academia, and students, really there's just this really long tail, few folks out here in the very highest levels of data size. So you're looking at over 100 petabytes. That's limited to a really small number of really big internet companies, government labs, people working on very specific big data projects. The majority of folks are right in this number of hundreds of gigabytes up to a terabyte of data. So what that means is it's manageable. You can do a lot of data science on a laptop. You don't have to go out and invest in giant hardware, hosted cloud systems. Given your use case, that might be the right way to go, but it's definitely not required to get started. So I want to make sure that message got out there. So when we talk about machine learning, this is a question I get a lot is what do you mean by machine learning? And kind of the best summary I've heard of that is that traditional modeling is taking data and rules to derive answers. And in machine learning, you're really flipping that around. You're saying, well, we don't really know what the rules are in this case. So we're going to take data and answers, and we're going to back into the rules. So we're going to figure out the rules from the data and the answers. And so what this means is we look at past observances, look at past incidents of the data type we're looking at, and trying to figure out what are the rules that describe how those occur, or how those groups form, or how that contamination spreads, whatever our problem is. And this is a little different approach than traditional modeling, which would say we're going to figure out the rules in a laboratory environment, and then we'll apply those rules to the real world using that data to make predictions. It's just a different approach. I sometimes think of them as traditional modeling is kind of top-down. We'll go from sort of top-down theory and propagate it out to the real world. And machine learning really starts at the real world. Here's what we observe in nature, and how do we derive rules from that. A common thing that we do in machine learning is pattern recognition. And so when I give this talk in front of a live audience, I'll ask, what are these pictures of? And people will say, there's a dog, there's a face, there's a bat, there's another face on the moon. And I say, no, this is a cloud, this is a clock, this is ink on the paper. So we're as humans, of course, I'm being a little facetious about it, but the word of the day is a term called apophenia. So apophenia is when we see patterns in our mind that aren't actually there. So we're sort of genetically predisposed to finding patterns because it helps solve problems in our everyday life. As we're trying to avoid danger or find opportunities, we want to find patterns and see things that are there. But it makes us more susceptible to getting fooled, because there are things that might look like or look similar to a face or something that isn't actually real. And so we have to watch out for that in data science too, because if we go looking for patterns, we'll find them, whether they're real or not. And so you have to be very careful about that, do lots of testing, and make sure that you're not fooling yourself into thinking that an early pattern that you see is the one that you really latch onto and believe for the rest of the time that you're working on it. So there's kind of a tree of families of methods here. So when we start getting into data science, one of the first things that we do is distinguish between supervised and unsupervised learning. So in order to learn from data, there are two different kind of major classes of problems. Supervised learning means that we have data that's labeled. So we have sites that are contaminated, sites that are not contaminated. And we've already applied that label, and now we want to be able to come up with the rules that help describe how we can distinguish between those two. The other one would be is we just have a lot of different sites and we don't know anything about them. We just want to do clustering and find groups within those. So there's a whole series of techniques that you can use. And any data scientist that's been at it a while or gone through a degree program or something like that, certificate program in data science, will be familiar with all of these. And these are sort of like tools in the toolbox. So in our work, we do a lot with ensemble methods, decision trees, neural networks, Gaussian mixture models. Those are the naive Bayes. Those are tools that we use quite a bit in our work. And we've found that they are a pretty good place to start. A particular type of decision tree called a random forest model is in particular a pretty good place to start for any problem. You know, it gives you pretty good results without a lot of work. And so that's typically where we start, and then we can kind of move from there and you know, choose techniques that are proper fit for the problem we're working on. Under people, you want to try to find the right people for your unique business objectives. And there are these different competing, not necessarily competing, but different focus areas that people will have. So you might have people that are really good at statistics, or really good at data wrangling, or really good at coding, and then to the strength of their skills in those areas, I kind of break those up into different people. So we have this persona of a mechanic who's really great at data wrangling. They can get data from one place to another, do any kind of transform you want. And then you have people who are really good at statistics and not really good at the implementation part. They're more of the academic flavor. And so this gives me a map to kind of judge people's skills and how they fit into the overall environment. And you need a mix of all of these, I think, to really get a team that is proficient. But don't forget some of the soft skills as well. So we have design, communication, and customer focus. Design can be really important in everything from creating GIS and CAD maps to our statistical charts and tables to communicate with our customers. If we create this great data science product and do a predictive analysis, but we can't communicate it, then we've not done any good to anybody. So we have these kind of personas here. So the person with the A+ communication skill could be our evangelist. The absolute best design person might be the artist. And then the customer focused person might be a sales engineer. And there are lots of different personas in between based on their balance of skills. When you bring data science into an organization, there's something that I call the new challenge. So you have people with a lot of time in the company, and you have people who are working with process maturity. If you have both of those, you're almost on autopilot. So you've been doing it a long time. The process is really hammered down. You can really crank through that and make process improvements. But if you're working on a relatively young process, so if you're just bringing data science into your organization, so it's relatively new, and you're bringing new people in to do it, you have people with very little time in the company doing a brand new thing for the company, they're kind of viewed as outsiders. And so I typically don't recommend that. So you can either grow up the data science skills from within your company with people that are there, or you can hire in people that are already really well-versed in your organization, but have that data science skill. And those can be that kind of pioneer persona. So they've been with the company a long time, but they're taking the company in a new direction, adding a new innovative technique to that company. So they take that pioneer persona. I won't spend a ton of time on hardware, but I wanted to talk about two aspects of it, processing and storage. There's a quote that I love is when I look at somebody's problem and they're using a lot of big data hardware, distributed computing, tons of machinery on Amazon, and I say your data fits in memory. So if all of your data fits in memory, then you can run it on a single machine, a laptop, a desktop, and you don't need to necessarily distribute it. Distributing amongst a lot of computers, especially on something like Amazon Web Services, comes with a lot of overhead. And so it can actually slow down rather than speed up your process. So this is just an example of that. So single thread here represents a single computer working on a problem versus distributed Spark. These are just different big data architectures. So you can think of them as different databases, whereas this is just running on a single thread on a laptop. And notice that the time to run these operations is faster in most cases than the big data systems. And that's directly tied to the overhead of communicating between 128 different machines. There's also the cost of storage. So I've been keeping these stats since 2011. And this is the cost of storing a petabyte of data. Most of us don't use petabytes, but it's a kind of a nice round number when you're talking about storage costs. So just to buy the drives, the hard drives to store a petabyte of data in 2011 cost $120,000. If you wanted to host that same data on Amazon, it cost $1.7 million. In the time since then, at the latest numbers that I have, the cost to host it on Amazon now is the same as it was for the raw drives back in 2011. So it's come down to $120,000 with the same capabilities. So the price is coming down every year. There are drops in prices on storage and processing for hosted systems, but it's something to be aware of. The other thing that, it's not totally apples to oranges is that these middle, so that this is the raw drives, that doesn't give you any computation. That's just hard drives sitting in a box. Supermicro, Dell, and NetApp are all hardware manufacturers. So that would be like an on-premise solution where you have your own data center, you have your own server room, and you can plop this in there. But that doesn't count power, air conditioning, square footage, rent, things like that. So, and then the Amazon doesn't have those. This is kind of your all-in price. So it's not exactly apples to oranges, but I wanted to give you, or apples to apples, but I wanted to give you a sense of the cost of storing that much data should you need it. And then there's software. This is the latest published poll from an organization that's been doing this poll for a while, since about the same time period, I think 2012. So the latest version, we have the last 3 years numbers. So some of the top tools that people are using for data science, Python is a programming language, scripting language that has lots of add-ons and libraries for data science that you can bring in. It's definitely the most popular. This one, RapidMiner, is a graphical data science tool. So it's less for coding and programming than dragging and dropping and connecting up different operations in kind of a dashboard view. It's being used in a lot of academic settings, and I think that's led to its rise in the last several years. So I haven't encountered this too much in my professional life, but I've seen it in academia. I think that's related to the rise in the last few years. And then R is another language that's statistical programming language, very similar to Python, similar types of libraries, but not quite as tied into the research that's going on in the latest data science techniques. So I think that's why you're seeing Python up here. But something that I always am kind of interested to see is that Excel is right up there. So just because Excel is an office product and something that people use for spreadsheets and accounting doesn't mean you can't do some data science with it. It has plugins for data science. It also has lots of built-in functions that you can use and even extend yourself through scripting with VBScript and things. So don't overlook Excel either. It's also probably the most common data interchange format. If you ask for data from people, they're probably giving it to you in Excel. So it's going to be important to learn that. On cost, does your organization have the bandwidth to support a data science project now? what other activities would you have to give up in order to invest in a data science project? So it comes out into this build versus buy scenario. And so a lot of times I'll help companies understand the total cost of ownership. So if they wanted to build something in-house, it doesn't mean just building it. It's maintaining it and keeping it around so that you can use it on into the future. And is that something you can commit to, or do you want a third party to do that and buy the solution either from a product or a services vendor? So in my own examples, 3D groundwater data was deemed too high a cost to accomplish in-house with the resources that we had. So we were able to go and outsource a team that we recruited and we hired to build up our data collection in that. But on the other hand, doing statistical models for contaminant concentration also required a lot of effort and a lot of time, but it was core to our competitive advantage. So we wanted to develop that in-house. So that's the kind of decision criteria you have to think through when you're starting down the data science road, is how much of it do you want to do in-house versus outsource, and what types of resources do you need? Okay, so I want to show you some specific examples on a tool that we created called Invimetric. This is a data science tool that's used to predict the most likely extent of underground contamination using a machine learning model. And so I'll walk through how we do that. So the inputs that we get for Invimetric come initially from our clients, and we really just need an initial concentration, a source zone location, and some groundwater information to the extent that they have it. If a full groundwater elevation survey has been done, we'll take that. If we only have the surface terrain, we'll take that as well, and there's some interpolation that we can do to make an estimate on the groundwater. And then we compare it to our database that we have of sites that we've collected from across the country. So currently we have about 85,000 sites in our database. So these are contaminated sites where an initial conceptual site model has been done. Most of them have gone into remediation, and we have some statistics on what was done there and how large that contaminated area was deemed to be. So of the 85,000, that information is usually in PDFs, Excel documents, web pages, things like that. So it's not in a ready state where we can really pull it in for data science. So we have to go through some processes in order to do the data engineering and data extraction in order to be able to use that. So the types of information we collect on each one, so we'll do the 3D contaminant extent. And so we have to go in and look at that report, see where the data was collected, what the initial conceptual site model said, or the one we try to get to is the last one right before remediation started. So if they did multiple assessments and it evolved over time, we want to find the one that's the most current before any remediation action was started. The source zone location in 3 dimensions, we have the XY location and the depth, contaminant type, maximum contaminant concentrations, hydrogeology data, depth of water. You can see the rest of them there, conductivity, geologic profile, and then other parameters that we can collect on that site. So Anna, I think we have another poll question queued up. I might need to, I can't tell if I can see this or not, but there we go. Okay, I see it this time. Okay, so we wanted to do a quick poll question just to see, so we know what the most common types of sites are in our database, but we're curious if that also matches up with your experience. So of the options that you see there, DNAPL, LNAPL, heavy metals, emerging contaminants, or other, what's the one that you work on most, the one that you see the most often? Okay, great. Yeah, so this is a little surprising. So folks that are working on DNAPL more than anything else, the vast majority of data from the States is actually LNAPL, but it looks like you folks are, I guess what I can attribute to is that you're forward-leaning, you're working on really complex sites, and so you're looking for techniques that are related to data science that might help with that. The DNAPL sites tend to be a little more complex. A good portion of heavy metals and emerging compounds too, so probably some PFAS and things like that in there. Okay, great. Thank you very much. It's good info. So what we have to do when we go in and we look at each of those sites and we collect that information We call that our augmented sites. And so from that 58,000, we now have almost 7,000 sites from across the country, focused mainly in Southeast U.S., Mid-Atlantic area, and in the West Coast and mountain regions. So those are the sites that we can actually run our data analytics, our machine learning process on. Now that we've done that data prep, and it's a huge level of effort. I mean, data scientists will tell you that, despite learning everything they can about the latest methods and going to conferences and doing the math and doing the programming, it's really this data cleaning that's kind of the biggest challenge or the biggest component of their jobs. I've heard as much as 80%. That's just this, but it's an important thing. Everybody's data is messy, and so it takes work to get through it. So once we have all this information, now we can use our machine learning models to start to filter through it and understand which variables are important to predicting the size of our plume, our contaminated area. And so we let our AI engine determine those decision rules. So this is kind of a view of the tree of all the decisions that the AI makes when it's looking at all of the variables that are there in order to come up with an answer for the predicted plume length, width, and depth. And so I'll show you what that looks like. So we take this contaminated volume area and we're trying to predict the bounds on that. What's our outside bounds, and we can do it in terms of percentages or percentiles. So our 50th percentile plume length would be the volume that contains 50% of all plumes that we've seen. Those extreme events, the really large plumes in the database, are going to be out at the 95th percentile area. And so we can create these tables that are specific to a particular site, but also show context with similar contaminants, similar ones in its area, in its geographic region, and things like that. So this is what we'll produce in that infometric report. So the table gives you one view of the information. There's also this distribution. So these curves here show the length of the plume, and then the range of estimates that's created from the infometric models. So we're using this information to tune and also to predict where that plume is located for sites where we don't have the answer yet. Okay, so we do that for the length of the plume, the width, and the depth. And so we can come up with metrics or summary statistics on all of the plumes in our database. You may have seen a blog post we did a few weeks ago that said for all the sites in the United States, here are the percent that are larger than putting green or football field, things like that, to kind of give us an idea of the context of how abnormal or how large is our site compared to other similar sites in that area that have similar characteristics. Then we take that information and we visualize it in GIS and a 3D viewer. And we provide metrics of performance. So the measures of performance are related to true positive, false positive, and false negative. And then everything else out here in the rest of the world is what we call true negative. So that's not really important to calculate. It's these other values. So if the oval or ellipse shape here is our forecast and the irregular shape is the actual plume, anything in this blue area is false positive. Those are things that we called plume area that actually was not. So that's a false positive area. True positive is where they match up. And then areas where we predicted the plume, but it wasn't actually there, that's a false negative. So we were able to, actually I've got those reversed, don't I? No, false negative. So we predicted the plume, but the actual plume went outside of that area. It was false negative. So we said there wasn't plume. And then from those different numbers, we can calculate precision and recall, which are common metrics for evaluating decision models or data science models. So we have a quick little case study I'll show you we did on the Jadco Hughes site. So Jadco Hughes is a facility in North Carolina. It's an EPA Superfund site. They stored chemical waste there for a number of years, and it was a solvent reclamation site in the 70s. And so it was a pretty bad site. They had a lot of spillage there. And in '86, it was added to the Superfund priority list for remediation. So what we did for this site is we modeled the distribution of the down gradient distances. And so you'll see that these numbers are cumulative. So the probability that the plume is entirely contained within the 0 to 50 meter range is 23%. And then as we go down and we get farther and farther out and our range extends, those individual probabilities get smaller, but they're cumulative. And so everything within the 350 meter range, we're at 92% cumulative probability that that's our confidence that we've contained all of that contaminated volume. And then we can take the output of the model and project it back onto the site. And then those rings, those range rings, represent those probability bands of everything from 50% up to 95 or 99%. If you want to learn more information about this, there's a link here, and it's also available on our website at azimuth1.com. So the precision metrics that we had here, so everything that we had in the contaminated area that was also contained in the model output, we had a 95.6% match there. 58% of the not contaminated area that was contained in our model was primarily due to there was kind of a curvature in what was happening at Jetco Hughes, and our ellipse encompassed everything, but there's sort of a carve out there, and so we had a little extra not contaminated area that was included in our forecast. And then we only missed 4.3% of the contaminated area that wasn't included in the model. So for this particular model, we see a couple of different use cases here. One is early investigation. So you can use this to project onto a new site that you're just starting and you need help working on a collection plan, investigation plan. We can tell you what the statistical likelihood is without ever doing any field work there. So for folks that maybe aren't able to do field work now or are seeing less of that, this might give you a way to get a jump on it so that when you are able to go back out in the field, you can see where those high probability areas are. Another use case is when you have data gaps because of lack of access. So the model doesn't care where the property bounds are or whose property it is. It just tells you the likelihood based on groundwater conditions and contaminant concentrations there. So even if you're not able to get onto a neighboring property, the model will be able to extend there and tell you the likelihood that it's actually on that property or coming from that property. And then source zone identification. We didn't talk about it in this just out of consideration of time, but we showed the downstream model. There's also an upstream model. So if you don't know where the source zone is, but you have a contaminated detection, then you can work it upstream and say, here are where the possible source zones are. And if you have candidate source zones, we can apply a probability to each of those and say, here's the probability that the contaminant you see at point A is coming from source zones X, Y, and Z. And there is one poll on this site. If Anna, you can fire that one off. Okay, so of these three applications of machine learning, what's the most relevant to your workload? Okay, data gaps is pretty popular, 52% there, early investigation, then source zone identification, and then other. Great, thank you very much. So for wrapping up, so here are some best practices and next steps. So these are recommendations for me just based on my career and working with other companies and teams and doing data science. Define the problem first, not the data. So if you go, the worst mistake that people can make in doing a data science project is they go and gather a bunch of data and they put people in a room that are separate from the organization and say, okay, go find some patterns in the data. Those people are going to get really excited and come back with patterns that are totally meaningless and have no bearing on your business processes or the goals you're trying to achieve. So define the problem first, make sure it aligns with your organization's goals, then let that guide you in what data you need to collect. Have a balanced team with a mix of technical, scientific, and communication skills. Think about how to get your organization to the next level in that data science pyramid. If you're just doing kind of the basics of collecting data, try to get up into that analytics tier. If you're doing analytics, try to get into the automation tier to help you get further up that food chain. To improve your analytics performance, first add more data, then add more variables, then go for more methods. Don't do it the other way around. And then always get context around the problem. If you're working on one particular difficult site, we found it can be immensely helpful to get information from other sites that have similar characteristics that aren't the exact one you're going through. It gives you context for, what should I expect, all else being equal, from this site. It can help give you another line of evidence. And then just a quick pitch, we can help. We offer custom data science services and products tailored to site investigation and remediation. So, please contact us if you would like our help or just want to give us some feedback. There's also time for questions. So you can drop your questions in the chat and they'll get relayed to me. You can also find out more info at our links on the screen. All right, well, thank you, folks. If there are any other questions, we can take those. But really appreciate your time, appreciate you jumping on here. Stay safe, stay healthy, and thanks for coming in, and feel free to give us any feedback via email or hit us up on our website either way.